Hi there and welcome to Pluralsight. This is Tim Warner, as usual, welcoming you to the module entitled Network Architecture Devices. Let's buzz through our Pluralsight learning path for the CompTIA A+ 220901 certification exam. Learning path, as you know, is a series of courses which cover every single objective for a given IT certification test. Our first course in this learning path is called Introduction. Then we have a course devoted to hardware. That makes sense when we consider that the A+ is a PC repair credential. Networking, that's where we are right now. Then we have mobile devices and troubleshooting. In our networking course, I've divided it into 8 modules. Again, you can cross-check these against the A+ objectives published by CompTIA. Visit comptia.org for details. The first module dealt with cables and connectors. Then we did 2 modules on TCP-IP, one on basics, the other on ports and protocols. We spent time with wireless networking, of course, then small office, home office networking, internet connection types. Today we're concerned with network architecture devices, and the final module is called networking tools. What are we going to learn in this module? Well, I want you to understand the difference between the basic network infrastructure devices. So we're going to start at the beginning with the hub and then move our way through the bridge, the switch, the router, and so forth. We've referenced these devices quite a bit throughout this course. I think that this is going to be an edifying module for you because now we can actually deeply understand each of these devices in the context of the TCP/IP protocol suite and the OSI reference model. So related network device concept sounds like a potpourri if you've ever watched the game show Jeopardy! And that's kind of what it is. We'll discuss things like power over Ethernet and power over Ethernet injectors. There's some good stuff in this module. I'm glad to teach it to you. Let's get started. Meanwhile, in the real world, as a certified A+ repair technician, you might be asked, does anybody use modems anymore? The old analog dial-up modems. Now, just the fact that we have the question here is leading toward an answer, but we'll formally answer it at the end of the module. Secondly, and this is a question that, again, you're going to get from somebody with some technical background. Maybe they're studying for their A+ or Network Plus exam, and they ask you, I understand that a switch operates at OSI Layer 2, but I'm seeing references to a Layer 3 switch. I thought that routers operated at Layer 3. What's the deal? Once again, if you feel a little confused right now, hang on to your hat and study up, because we'll revisit these at the end of the module and you'll understand exactly the concepts at play. Here's our specific CompTIA A+ 220901 learning goal. It's 2.8, which says compare and contrast network architecture devices, their functions and features. Network device Roundup. As I said, we're going to take network connectivity devices from soup to nuts, beginning with the antiquated hub. You see a Netgear model off on the right here. Now, you're going to have to look quite hard to find a hub nowadays. They've been supplanted by the switch for many years now. A hub is a means of connecting computers on an Ethernet network segment that operates on OSI Layer 1, physical. Now, you'll remember that at the physical layer, data is represented as zeros and ones, just bits. You can look at a hub as a multi-port repeater because every device that's plugged into a hub can theoretically communicate with each other. That's true. And it's also true that the signal is regenerated or repeated at the hub. So hubs are sometimes used to extend a network. Remember that Ethernet cable has a limitation. At least the copper twisted pair Ethernet cable has a 100-meter segment length limitation. But the reason why I say that hubs are dinosaurs, that you don't really use them anymore, is because the hub represents a great big collision domain. Any device that's plugged into a hub, they're all sharing the same bandwidth in the circuitry of the hub, and those Ethernet frames can smack into each other. Now, the original Ethernet spec accounted for collisions. See our course at the Pluralsight library on Network Plus for more information about that. Or you could do a site search for CDMA-CA, but that's not the point. Once the switch came to the forefront in networking and the price of switches came down, they've totally eradicated the hub from the business landscape, because the bottom line is you don't want those collisions taking place. networks, and a collision takes place when two stations both put Ethernet frames on the same shared medium at the same time. It wastes time and it's inefficient. Now, hubs do actually have a purpose in 2015 and 2016. You'll find that some network technicians keep a small hub in their tool bag for diagnostics purposes. It's actually a good thing if you're using a tool like Wireshark and you want to sniff network traffic at the frame level, to have a hub and to put the machines that you want to monitor into a hub rather than a switch, because as we're going to learn in just a moment, a switch actually separates each port into its own collision domain, so it makes it more difficult for you to sniff traffic from other stations. Now, I've mentioned a switch several times, and I've mentioned that they're the standard nowadays. That's true. The switch is a network connectivity device that succeeds not only the hub, but also the bridge. There was a stopgap device back in the day called the bridge that served as a way to segment one collision domain into, say, two collision domains. But once again, the bridge has largely gone the way of the dodo because the costs involved in creating switches has come down to the point where, and you know this, you can buy a consumer class wireless access point that has a built-in 4-point switch. You can go to your local electronics store and purchase an 8-port or a 16-port switch for a very reasonable amount of money. They're very common. Now, it's important to note that these switches use dedicated hardware circuitry, what are called ASICs, application-specific integrated circuits, to do their work so that they are very highly performing. Switches are more intelligent than hubs because they operate at OSI layer 2, or the data link layer. Remember that we're concerned with the Ethernet frame at layer 2. And you remember what kind of addresses are used at layer 2? The media access control, or MAC hardware addresses. So what the switch can do is store a table in its memory of all of the MAC addresses of all stations to which it's directly connected. Now, this Cisco Catalyst 3750 switch that you see down below has a lot of ports. Let's see. Oh, I don't even want to count how many ports those are. But the switch will keep track of the MAC address of any station that you plug into any of those switch ports, and therefore it makes communication much faster, because if one host on one port needs to communicate with another host on another port, the switch can immediately, switch that data stream to the appropriate port. Now, the problem with switches, or one problem I should say, is that if the switch receives Ethernet frames that contain, say, a broadcast MAC address, which is all Fs and hexadecimal, or if it's a MAC address of a station that the switch doesn't recognize, then it's going to flood the packets out of all its ports. So while switches can create separate collision domains, one per port, you still have one broadcast domain. So that's the limitation, the chief limitation of layer 2, and that's where the router comes in at OSI layer 3. Now, switches nowadays, in particular business switches, you're going to pay a premium for this functionality, can have plug-in router modules that give a layer 2 switch the ability to do layer 3 routing. That's beyond our scope here. I'm just mentioning this for your reference. So to sum up everything I've taught you about the switch, they use an in-memory MAC table and application-specific integrated circuits to provide dedicated bandwidth to every port. So on this switch, if those main ports are 100 megabit per second ports, then every single switch port can provide a full 100 megabits per second to a connected device. Remember that a hub is going to provide that 100 megabits across all ports. Not very efficient. CompTIA does want us to know just a little bit more about the bridge. I mentioned that the switch is the successor to both the hub and the bridge. Basically, a bridge is a 2-port switch. It operates at layer 2, but back in the days when those application-specific integrated circuits were more expensive, these bridges represented kind of an avant-garde, cutting-edge technology. More recently, a bridge would be considered a gateway, where you're switching from one network architecture to another. Before Ethernet became the standard, for instance, there were other network architectures, if you can believe it, like DECnet and ArcNet and AppleTalk and different protocols and architectures that basically competed. Token ring would be another one that competed with Ethernet. And if you had one token ring segment and one, say, 10^2 Ethernet segment, you needed some sort of gateway device in order to, bridge traffic between those architectures. Now in 2015, 2016, you might find what are called Wi-Fi bridges or workgroup bridges like this Linksys that you see at the left. Now, at first blush, you see the antenna and you think, well, this is just an access point. Not exactly. What this is used for, it's a special use case. You might have a pod or a section of wired hosts. Maybe you have in your office, the accounting department is so far away from the rest of the network, and maybe the way the building has been wired, that you can't easily connect from the rest of the office out to that remote office way down at the end of the hall. You could feasibly plug all of those wired hosts that use twisted pair cable into a Wi-Fi bridge and then give them all access to your Wi-Fi network. Admittedly, that's a special use case, but know that it exists. Even routers. Back when I got into IT in 1997 or so, routers represented a substantial investment, period. But nowadays, even small office, home office, and residential customers, or end users, let's say, consider their cable modem just to be as common as, say, a microwave oven. But that cable modem isn't so much a modem as a router, a device that operates at OSI layer 3, uses IP addresses to do its routing, and is responsible for shuttling network traffic to different segments. So the router actually can separate broadcast domains. Now you might think, well, if we have a business network, we have a router that we use to connect to the internet. Yeah, well, that makes sense. We're separating our internal private network from the public internet. But I want you to know that as a business gets larger and larger, actually even small to medium-sized businesses, I found that this is standard. You're going to want to segment your network into multiple subnetworks or subnets, each representing its own broadcast domain. For instance, you might create one or more subnets for your Wi-Fi traffic. Maybe you have a guest Wi-Fi as well as an employee Wi-Fi. And as far as your wired Ethernet, you may have a separate VLAN or virtual LAN as they're called for your IP phones and another one for your servers. You see what I mean? So it's pretty easy as long as you have at least one layer 3 router to segment your network. And when you segment a network, you're isolating the network traffic and you're able to apply things like quality of service and network security policies to each one of those subnetworks, okay? Routers, especially those made by the big manufacturers like Cisco. This is a Cisco 7201 that you see on the screen. Now, they have modular designs where you can just plug in modules that contain the interfaces and the functionalities that you want. Same goes for switches, actually. I want to revisit that concept of the Ethernet domain. Ethernet is the standard way to do data networking both at the local area network as well as the wide area network. And I've mentioned several times that the hub operates on a single collision domain. And what that means is that all connected stations share the same bandwidth, they share the same media, and when those stations kick out Ethernet frames, they have the potential to bang into each other, which means that the stations get notified that there was an error. They wait a random amount of time and then attempt to retransmit. Not very efficient. A switch, again to repeat, separates each switch port into its own collision domain, so you effectively never have to worry about those sorts of errors. The switch, on the other hand, does have everything in a single broadcast domain, so unless the switch knows the exact MAC address to where it needs to shuttle a packet, it's going to put those packets, frames, and data across all ports, and that's called port flooding and can create what's called broadcast storms that ultimately reduces the efficiency and speed of your network. The router separates not only the collision domains, that's handled by the switch, but also can create entirely discrete broadcast domains to which you apply policy. Now notice I did a little fill in the blank here. You might be asked on your A+ exam to count how many broadcast or collision domains you have based on what kind of Ethernet architecture you have with switches and routers. I said that there's 4 broadcast domains. How many collision domains are there? Well, there's 16, aren't there? A wireless access point is indeed a network connectivity device. I hope you see that the theme we've been working with throughout this module is we're looking at various pieces of hardware whose responsibility is to connect multiple stations together for the purpose of data interchange. The WAP, or the AP, I call them WAPs, but some people call them APs, your mileage may vary, provides connectivity using the IEEE 802.11 Wi-Fi standard. You need to know for your A+ exam what power over Ethernet is, or PoE. Imagine you are tasked with mounting a wireless access point in a conference room. And let's say the conference room has a huge, tall ceiling, and you want to put the access point way up in the rafters where nobody can see it. Maybe this business is especially concerned with cosmetics. Well, you can get the AP up there and you can secure it, and you can even run an Ethernet cable to it. But how the heck are you going to provide AC power? Are you going to have to spend money and hire an electrician? Not necessarily. You can use the power over Ethernet standard as long as you have the correct hardware to power that access point without having to run separate AC. It's a beautiful thing. We'll talk more about PoE separately. All I will say right now is that the PoE standard's defined also by the IEEE, and it provides 15.4 watts of power. That's good for low-power devices like smaller access points, IP cameras, or IP phones. If you're going to deploy multiple APs throughout your business, you might want to consider purchasing a wireless LAN controller. It's a rack-mounted piece of hardware that enables you to wrangle and control all of your APs. Another neat thing about wireless controllers is that when you bring up an AP, you can send the configuration directly to the AP over the network from the controller, so you don't have to repeat yourself over and over. There's an important principle of software development called DRY, don't repeat yourself. I think that also works just as well for us IT pros. Analog modem. Boy, we're really stepping back and forth through history here, aren't we? An analog modem, and we've covered some of this, I know, in previous modules. Please understand that I know that. The reason why I feel comfortable repeating it here is for two reasons. One, I believe as an educator, repetition is good in adult education. And number two, the more you hear this stuff, the quicker you'll be able to come up with the correct answer when you sit down to take and pass the CompTIA A+ 22901 certification exam. Now then, let me get off my soapbox and let's resume our regularly scheduled programming, okay? So, a modem, coming from the name modem, modulates digital signals to analog and vice versa. Right, we understand that. The right, we have both an external US robotics modem. I had one of these. They would plug into your computer using an RS-232 serial cable, if you can believe it. And then down below, an internal modem that you can still buy nowadays, believe it or not, using PCIe or old school PCI. Believe it or not, modems can have a purpose today in business. For instance, you may have industrial equipment, old equipment, that is already working. Maybe it needs to phone home or transmit diagnostic data in the middle of the night. It just places a very brief phone call, and you might already have a dedicated phone line connected to a little modem card in that device. And there's the principle, if it ain't broke, don't fix it. It's working, it's doing its job, so you're going to keep it. And frankly, I was doing a little research on this yesterday. There is a significant portion of the world that doesn't have access to high-speed internet. Living in the United States, it's easy, too easy, I think, for me to take for granted high-speed internet access. But for those people who live in areas of the world where dial-up is still the standard, I'm glad that we have the technology available. A firewall. Now we're getting into some of the more specialized network connectivity equipment. Now so far, the hub, the switch, those deal with aggregating network connections so users can get all on the same network. The router, as we know, connects different networks to each other. The firewall is a special purpose appliance. First of all, the fact that I said appliance is partially true because any operating system worth its salt now is going to have firewall software built in, but the hardware kind again has the advantage of dedicated integrated circuits that make for performance and scalability. Now, what the heck does a firewall actually do, you're probably wondering? A firewall selectively allows or blocks network traffic. As far as inbound traffic into your network from outside the network, you want to be highly selective. Generally speaking, you're more relaxed inside your network perimeter because you have control of that infrastructure. So you poke holes in your firewall, that's the colloquial expression, by writing rules to selectively open ports and IP addresses on your firewall to make traffic secure. A packet filtering firewall operates with rules that use just those exact metrics, IP addresses and port numbers. However, if you want to pay a little bit more money, and in a business to protect your network, you absolutely do, you want to consider a stateful packet inspection or SPI firewall. These are cool because instead of looking at the IP address and the TCP versus UDP issue, the port number issue, you know what OSI layers those are? Well, the TCP UDP ports is layer 4, remember, the transport layer, and IP addresses, of course, is layer 3. SPI can actually go up to layer 7. Remember that layer 7 is the application, where the firewall can actually identify sessions and enforce rules on those sessions. So instead of just looking at the lower levels, IPs and ports, you can say, oh, I see that this person is using a BitTorrent application and they're attempting to create a session with this tracker, blah, 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 on the other side of the world. So the firewall can actually use much more intelligence in determining the kinds of traffic that are happening and then apply allow or block rules based on those. Related network device concepts. I have to say with some shame that this is one of the more vague lesson headings I've created. I must not have felt particularly inspired that day. A patch panel. This is important though, certainly. A patch panel is a cable termination point. Remember that a piece or a segment of twisted pair Ethernet cable is going to have some kind of end to it, right? I don't mean to get metaphysical on you, but on one end you're going to terminate into a user's computer, and then the computer's going to go through the walls, through the plenum, wherever, to the nearest wiring closet, and the other end of that cable almost always terminates into a patch panel. These offer modularity. Now what happens is, look at the bottom part of the picture. That's what's called a 110 block, and the color codes correspond to the IATF 568A or B standard, whatever you're using at your business, and we've discussed that earlier in this course actually. And then you use a punch-down tool to separate the 8 wires in the UTP cable, and then on the front piece of that is where the actual modular jacks are. Notice that there's a little spot for labeling. You definitely want to label each one of these patch panel ports with the Ethernet outlet that is on the other side of that cable. Companies that get lazy and don't do that wind up paying a big price in the future, so make sure you're documenting. But the modularity means that we can then patch any of those panels down into a switch, and if you need to switch a user from, well, I guess I made a pun, didn't I? But if you want to move a user from one switch port to another, the idea is all you have to do is move their patch from the one port on the switch to the other. It's really a beautiful thing. In the lower left, you see somebody using a punch-down tool. What you're actually doing is pressing the copper conductors in your cable down into copper terminals in the 110 block. Now, technically, what you're seeing on this slide is what's called a 66 block, and this is what's used with the RJ11 standard and telephones, but it works the same way as the 110 block does for RJ45 and Ethernet. A repeater or extender is a way to break the 100-meter barrier. Remember that Ethernet cable begins to attenuate or suffer serious signal loss once you get past that 328 feet or 100-meter barrier. If you absolutely need to run cable longer, you can regenerate the signal by plugging in a device like this. You'd plug in the one segment into the in port, and then you'd have another cable segment coming out, and it's cool because you get another 100 meters. So these do have their place. Notice that they are separately powered. Although that having been said, power over Ethernet can come into play, and you can actually power a repeater over Ethernet, which introduces a question why you do that. Well, remember the example I gave you earlier where you're mounting an access point high in the ceiling? You might not be able to get to that device with 100 meters of cable. So you may need to use a PoE supportable repeater or extender to regenerate the signal of both the data and the power capabilities of that cable, you see? Speaking of which, there's a couple power-related issues I want to go over with you. First, Ethernet over power. What's that? Didn't you say power over Ethernet, Tim? What's Ethernet over power? Are you playing word games? No, I don't know why CompTIA uses that term Ethernet over power. I call it power line Ethernet. And what you're doing with power line Ethernet is actually using mains power, AC power, in your business or home to do data networking. It's actually really cool. You can go nowadays up to 500 megabits per second. And it's useful for many reasons. You can use it to reduce cable clutter. You can use it to avoid having to run run cable in your plenum or through your walls or whatnot. I actually have power line running at my house. Look over on the right. We have one station that maybe is too far away from the telco closet, or you don't have wiring. You know, some businesses, as they rapidly expand, they start to break out workstations for users and then realize, whoops, we don't have an Ethernet drop available. What can we do? Well, we can plug in a power line adapter into the wall outlet. Don't put it into the circuit breaker device, put it right into the wall, and it'll have an RJ45 on it. So plug the user's computer into the power line adapter. You go through the mains power, come out on the other side with another power line adapter, and then into a switch or into the rest of your network, whatever you want to do. It's a beautiful, beautiful system. This is what a power line adapter looks like. Pretty easy. It just has LED indications on the front, whether it's powered, whether it's connected to a network, and so on. And then there's an RJ45. This plug is a 240 volt one, not a US one. But like I said, I use this at my home because our access point doesn't cover our entire home, so I mounted an extender upstairs. And to make sure that the extender and our main access point have a very reliable connection, I used Powerline. Power over Ethernet, formally speaking, is the IEEE 802.AF standard. Applications for PoE, this is where we're carrying power and data over the same medium, are devices like IP phones where you don't want to have what's called a wall wart blocking up an outlet. You can just run the power directly on the single Ethernet cable. I've already mentioned access points and IP cameras. Down at the bottom, this is a Catalyst 2960 switch. You want to make sure that the switches that you purchase, if you need PoE, support it. It looks like this one has 24 ports, all of which support power over Ethernet, which is a good thing. Now, there are other options like a power over Ethernet injector. An injector is used when you don't have a power over Ethernet capable switch. So you can purchase one of these little devices. They're pretty small. They look a lot like the repeater extenders that we saw a moment ago. And you can simply run a cable out of the non-PoE switch into the injector, out of the injector into your PoE capable device, and the injector is what supplies the power. That's good for one-off situations where you have maybe an access point or a single IP camera. But they're not good if you have a whole bunch of access points. That becomes a really big, messy mess. Well, what do you do then? Well, you'd buy a PoE switch, but there actually is a third option. A PoE midspan looks like a switch, kind of acts like a switch, but what you do is you uplink from your switch, your non-PoE switch, into your midspan, and then out of your midspan you can connect multiple PoE connections. In this demonstration, I want to show you a little bit of the application of technologies like layer 2 switching, layer 3 routing, and so forth. Now understand that you're not going to be held to know any of this stuff that I'm going to do here on your exam. You will on your Network Plus, but this goes well beyond A+, so just have a good time and enjoy flexing some of your new knowledge, okay? We're looking at a piece of software that I helped develop, I'm proud to say. This is the Cisco CCNA Routing and Switching Network Simulator from Pearson, and it enables you to do Cisco internetworking with virtual gear that acts exactly like the live counterparts without you having to actually purchase the routers and switches and so forth. So what we have in this topology is a router called R1. This is modeling a Cisco 2901 K9 router. We have a switch that's centrally connecting 3 hosts here. The switch is modeled on the Cisco 2960 integrated services switch. And you'll notice here we have 4 of the switch ports in use. Fast Ethernet 01, Fast Ethernet 02, and 03, and Gig 1. This particular switch has most of its ports using Fast Ethernet, which you know is 100 megabits per second, and it has a small handful of gigabit Ethernet switches. Now, a virtual LAN is also called a network segment. It's also called a separate broadcast domain. Again, I'm not going to get us into the weeds and the details here, but all you need to know is that the router is already configured to host 3 separate networks with 3 separate network IDs. They're going to be VLAN 1, 2, and 3. In this lab, I'm only going to create 1 VLAN. The way that the router and the switch operate and can pass all of that separate network traffic together is by means of yet another Ethernet standard called trunking. Again, we don't need to worry about that. All I want to show you is just the basic workflow on how you would set up a switch to support multiple VLANs or broadcast domains. The reason we would do that, remember, is so we can optimize network performance, cut down on broadcasts, and apply security policies. So to begin, why don't we come over to our switch. I'll double left click the switch. It looks like I'm already there. I'm using an operating system called the Cisco Internetwork Operating System, or iOS. Type enable to get into the privileged mode, and I'm going to do show VLAN brief to see what we've got going on with our ports. It looks like this switch is plain vanilla. It's got just one VLAN called default, and every one of its ports is on that single broadcast domain. So we should be able to, as long as all of three of these hosts have compatible IP addresses, be able to ping. And we can. Let's go over to PC1 by double-clicking it. I did an ipconfig /all, and I can see that my IP address is 192.168.1.2, and that my default gateway address, which is my near-side router IP address, remember, is 1.62. Let me try pinging that IP. So I'll do ping 192.168.1.62, and that came back fine. PC2 has an IP address of 1.3. and that came back just fine. S1 up there, server 1 has 1.1. I will not ping it. Let's come back to the switch, and we can easily create additional virtual local area networks. We're going to do configure terminal to move into configuration mode. You notice that the prompt changes on Cisco devices depending upon what mode you're in. To create a VLAN, check this out. VLAN 2. Simple as that. And I'm going to name it VLAN 2. Can you get any easier than that? Wow. Let me exit and do show VLAN brief. And we can now see that we have a new broadcast domain defined. Of course, you're going to have to think, do I have an interface on my router reserved for VLAN 2? And in this lab, you do actually. This product's cool because if you do all the labs, it walks you through the entire configuration from soup to nuts. To take PC1's port and put it on VLAN 2, it's fast Ethernet 0/1. I'm going to go back into configuration mode. The Cisco iOS allows you to abbreviate everything, which is pretty cool. I'm going to do interface FA01. Takes us into interface configuration mode. I'm going to say switch port mode access to say that this port is not a trunk port, it's a access port that's connected to a live host. And now I'm going to do switch port access VLAN 2. So now I've immediately placed PC1 on VLAN 2. Let me exit to save my changes. Now what that means is, because I'm still using a VLAN 1 IP address, will I be able to ping other hosts on other subnets? Now, because I haven't changed PC1's IP address, it's still a .1 that's being used by the rest of the network. Should I be able to ping PC2, which is 192.168.1.3. 192.168.1.3. Oh, it timed out. You see? So that's the broadcast domain issue in Technicolor. We've isolated PC1 onto its separate network. In order to rejoin it or reallow it to communicate with hosts elsewhere in this network, we're going to need to give it a new IP address as well as a new gateway IP. The router has the IP address 192.168.2.62 that's associated with VLAN 2. So I'm going to use a command. Now, this is where this simulator breaks down a little bit because it doesn't support graphical utilities. So in order to change a PC host's IP address, you use a command that really doesn't exist. There's no IP address command in Windows, but sometimes you have to work around it. So I've changed this device's IP address to 2.1, and I'm going to use the fake command gateway to specify the default gateway address of 2.62. And I can verify that by doing an ipconfig all. And now that I have a connection to the router, and the router knows how to get to all the different VLANs and all the different network segments that are there, I should be able to ping PC2, which again is at 192.168.1.3, and it goes through this time. So I hope that this was somewhat useful in terms of helping to illustrate how the layer 2 switch and the layer 3 router work. Now, back to the real world. Let's take a look at those questions. Does anybody use modems anymore? And what's a layer 3 switch? You should know these now and feel proud of yourself with your new knowledge. I mentioned that yes, sometimes remote users and those who live in parts of the world that don't have high-speed internet access need a modem. With layer 3 switches, we know that that's very capable if you have the money to spend. These are layer 2 switches with router modules on board. For your homework, I'd like you to consider the following questions. 1, how can you optimize the network connectivity at your home? Have you done a Wi-Fi survey to figure out where your coverage is? And if you decide you need an extender, maybe you can consider adding Powerline to the mix. Also, search eBay or whatever online auction house you like for low-cost networking devices. Consider building a practice lab. Software like the network simulator that I used in today's demo is really nice, but there's no substitute to actually putting your hands on physical hardware and cabling them up and going through the learning curve of getting them talking to each other. For further learning, check out, yes, Mr. Reference himself, Ross Bergertis, his network operations for CompTIA Network Plus, because what he covers in his NetOps course is a perfect supplement to what we did here. Also, Ben Piper's Practical Networking course is excellent. Again, the whole course is good, because he applies what we're learning in this course to a strictly troubleshooting context. And I want you to start getting into the troubleshooting mindset more, because the last course in this learning path actually is all about troubleshooting. In summary, you've probably heard the expression, there's an app for that. Well, there's a network device for that, or some kind of converter. That's been a theme throughout this entire learning path. If you need to go from PS2 to USB, there's a converter for that. If you need to convert from one network architecture to another, you can do that. I like the fact that, number one, if you know what you're going from and to, and number two, you can apply some Google foo, you can solve your problem. I want you to make sure that you understand which OSI layers and protocols are relevant to each device. That's really the key takeaway. The hub, layer 1, the bridge and the switch, layer 2, the routers, layer 3, the firewall can be layer 2, 3, 4, all the way up to 7, depending upon how sophisticated the firewall is, the access point, layer 2, etc. In our next module, we're going to cover networking tools. So I'm going to help you build out your PC repair toolkit. Of course, you're going to have your screwdrivers and all of your PC repair tools. I want to make sure you have the appropriate tools for network diagnostics and troubleshooting. I'll see you then. Thanks a lot for your participation.